Hi everyone, my name is Josue Nassar. I'm a PhD candidate from the Department of Electrical and Computer Engineering. I'm co-advised by Dr. Monica Bugadjo from ECE and Dr. Ilmami Park from Neurobiology and Behavior. And today I'll go over my research titled Tree-Structured Locally Linear Dynamic Models to Uproot Bayesian Neural Data Analysis. Okay, so a quick motivation. So the brain is the control center of the human body. Thanks to it, we can do complex tasks from dancing and singing to deriving complicated equations. It's ironic, though, that the brain is the organ that we know the least about. And this lack of knowledge has actually delayed the development of cures for brain diseases from schizophrenia to even neurological disorders like depression, for example. And one of the reasons why there's been such a lack of knowledge is the complexity of the brain. The brain is comprised of billions of neurons, and they all interact with one another through electrical impulses known as spikes. And so lately, there's been kind of an outpouring of research that suggests that these giant populations of neurons are actually driven by a low-dimensional dynamical system. So if you look at the picture on the right, you see that the first picture is just, we call them spike trains. So each of those little ticks is a spike firing. And what has been done is from this high-dimensional spike train, we can extract some low-dimensional dynamical system. And then from there, we can also, from it, learn the vector field as well. And understanding these low-dimensional dynamics gives insight into how the brain performs computation. So for example, there have been research that shows that from spike trains, you can figure out how the brain does tasks such as decision-making. And modern machine learning obviously is great and gives us a lot of tools for doing this, but there's kind of been two main issues with it. The first one is that modern machine learning does not use any prior knowledge. Essentially, most modern learning machine techniques are frequentist. The second one is modern machine learning doesn't really give you anything that's interpretable. So for example, you can take a very large and deep neural network, throw it at this, and sure, let's say you can extract these neural trajectories, but then you have to spend more time teasing something interpretable out of it. And so my research focuses on not only learning these dynamical systems that underlie these neural signals, but also presenting it in an interpretable way that people can understand. And so for this, we have created our own model called Tree-Structured Recurrent Switching Linear Dynamical Systems. And just to give you a high-level overview, basically what it does is you partition the space and get each space its own linear dynamics. And it also allows for you to get a multi-scale view. It's also fully Bayesian, so you can incorporate prior knowledge. And if you're interested, stop by my poster.